Hello everybody, I am Arnaud Temme. I work for Kansas State University here in Manhattan, Kansas, and I'm presenting today on behalf of myself and my co-authors, Jordan Watson and Nate Brownstein, my graduate students. And I'll talk about opportunities and challenges for disaggregating our US soil map using legacy data. And I do that with greatest appreciation for all of our project partners in this NRCS funded project. Matt Bromley, Joe Brennan, Jeff Helrick, for the various states that we worked in, along with Kevin Norwood, and then our partners also on the Kansas State side are much appreciated. I'm going to start this off by showing you this beautiful image of our sort of home study site that inspires much of my work. It's called the Flint Hills. It's one of the last remaining tallgrass prairies, and if I know you anything, if I know you a little bit, then all of you are now looking at this image and kind of thinking like which soil goes where and where would the vegetation be most dense and so on. And that's what we do too. You would probably already see or at least expect different soils in the gullies, different than, for instance, on the wide and broad ridges that we have. And you would be right. However, if we look at Sergo Online, then we see, and I'll help you see it, that there are very large polygons. In fact, there's one huge polygon that covers about half the map here. It's called the Benfield-Florence complex, which contains 3 or more soils in its complex description. So we see it, Sergo doesn't have it. It's very understandable because this is not an agriculturally productive area. There was, of course, a bit less interest in making these maps very detailed, and it's completely fine, except if we could do better, we would love to do better. We would love to provide a higher resolution map. It's not just in Kansas, in the Flint Hills, that we want to do that. It's across the nation, I think. If we look at the distribution of polygon sizes for every state, so Sergo polygon sizes, as I've done here, and also for the entire United States, that's the big black line, we see that states are very different from each other. Nevada and Utah, for instance, have giant polygons here on that logarithmic x-axis, whereas Indiana and Iowa have rather a bit smaller polygons. It's related to the landscape, it's related to the level of agricultural interest, I think, in those 4 states. But there are also within each state also vastly different polygon sizes that indicates to us that there is space for improvement. If we were able to make all these large polygons that sit on the right side of all of these 50 histograms and move them quite a bit further to the left, then we would be left over with a lot finer and a lot more detailed soil maps. If we could do that without sacrificing accuracy, then it would be really interesting. And so that is something that we're very interested in here. How to do that, though? One way would be traditional mapping, going out to the areas that we didn't give that much detail in before. Of course, that's constrained by manpower or person power and time. The ascendant technique, I would say, is digital soil mapping. It's something that my lab does as well. We're really excited about that on occasion. But that's a very data-hungry method. Regardless of which approach you take within digital soil mapping, and you know there are many, they all need a lot of data to work really well. And that is the constraint on that side. We would need oftentimes a lot of new pedon observations. A third possible method to improve and refine our soil maps is use computer simulations of the processes that form and change soils over long time scales within the landscape position that they're occupying, and make predictions that way. It's something I'm also really excited about, but that's definitely in its infancy. I personally use the Lorica model for that. But what I'll talk about today especially is using legacy data from existing Sergo map descriptions to disaggregate. And the question, of course, is, can this be done? Is there enough information? And can we increase resolution without sacrificing accuracy? And I'll talk about both of those today. The good thing about legacy data is they are here, and there are many of them. We have the block diagrams that we all know. We have also beautiful, very detailed descriptions of our complexes and associations, particularly where we are told the expectation of the relative occupancy of the individual components. We are told where components sit. and also on what kind of slope they are found. And so there's a lot of that information that we can use conceivably to make finer maps without having to go out and do new observations. And so what we have available is that landform information. Do I sit on a shoulder? Do I sit on a back slope? Do I sit on a floodplain? We have down on a cross slope shape information, we've got curvature, slope steepness information, and the percentage cover of components. So that's described. The great thing, of course, these days is that we have a very nice, detailed 10-meter resolution digital elevation model for the nation that allows us to characterize slope steepness and curvature for every location in the United States. Alaska is a little different, but essentially every location in the United States with really high accuracy, and maybe we can use that to assign soils. And that's the key approach that we took as well. We developed a method, and I should say Jordan Watson developed that method as part of his master's thesis, that reads the SSURGO geodatabase, that reads the national elevation data set for the same region, that does a few tricks with that digital elevation model, aggregates it to several other forms, and then determines whether and how to split soil map units based on the SSURGO information. Are there different components within a complex that actually occupy different landscape positions so that we can tease them apart and make a finer resolution map? And then step 5 is the actual making of that map and providing the output back to SSURGO geodatabase format. There's a lot more detail you can imagine. If you want more detail, please ask me a question or check out Jordan's poster also later in the conference. We're currently providing this as an ArcPro tool, soon perhaps also as an ArcPro service, in which case you could actually access this for yourself and try it out without us being intermediaries. In visual form, this is really all that we do, although this is thousands of lines of code, I promise. We look at the description of map units in SSURGO. In this case, this map unit A has 3 components. We read the description of those components. We use auxiliary information, in this case the slope steepness map of the digital elevation model, and we use that to connect soils to slope position and then make a much finer resolution map. It does work in the sense that we are able to disaggregate existing SSURGO maps to much finer resolution, and I'll show you an example right here for Mason County, Michigan, one of our study areas. On the left, the original SSURGO map, different colors, different soils. You see political boundaries reflected in there. That's not something that we are able to fix since we just take legacy data. We take SSURGO as it is. But if you look on the right, within each of those original colored polygons, you now hopefully see different shades. It's especially apparent over here. And let me zoom in a little bit for you. It shows better now. I think that we have different shades within each of the original polygons, and that is the result of our process. We have disaggregated, in most cases, 2 different components into individual locations within the original soil map unit polygon. Of course, the real question now becomes, what did that do to the resolution and what did that do to the accuracy? So for the resolution, we see a drastic increase in resolution, a drastically finer resolution. We have the histogram here of the original, the pre-disaggregation SSURGO polygons in dark blue, and in light green we have the disaggregated resolution, and clearly we are looking at much smaller polygons. So that's a great sign, I think. In terms of accuracy, we've calculated accuracy using the formula up here, excuse me, which basically says if you make an observation of a certain soil series in a certain location, we are going to look what percentage of the area of the polygon that that observation is in was predicted to have that soil. Sometimes that percentage is 100%. That's great. Then SSURGO did a fantastic job. Very often that percentage is a bit smaller, and in that case SSURGO gets a fractional score. We average all of those scores out over all the points we have available, and then SSURGO for Mason County, Michigan scores 42% accuracy. The disaggregated map that we make is basically the same. We are not sacrificing any accuracy while at the same time providing this much finer resolution. So that makes us really happy. We have 2 versions that we're currently playing with a little bit. This version 2 makes me a bit more excited. It's actually an improvement in accuracy, seemingly, for the randomly distributed points that we trust best. So no loss of accuracy, I think is fair to say, but also not clear gain for the moment. The way forward for us is, of course, we're going to deliver these results of the project. We're going to try and publish that as well, but nothing honestly stands in the way of disaggregating the entire country's SSURGO in this way. There is already information. We don't need any new information. That's the beauty of this approach, I find. We're not inventing anything. We're not measuring new things. We're simply taking what's there and making it better, I think. And so we're looking for partners with kind of county-sized regions that we can test the method out for before we try and upscale that for the entire nation. We're definitely really eager to push this forward because it's so promising as far as I'm concerned. So with that, thank you very much for your attention. We're able to take questions, at least I think so. I hope so. That's it.